Welcome back, everybody. In this section, 1.2, we'll be looking at how to find the domain and range of a function. So first of all, a definition. The domain of a function f is the largest set of real numbers x for which f of x is defined as a real number. So in short, basically what the domain is the set of inputs to a function. Okay, a way to keep that straight is to notice that the last two letters of the word domain spell out in. So the domain is the inputs of a function. So a couple of examples. Here we have a function f written out by a list of ordered pairs, 2, 1, 5, 3, and 6, 4. So if we wanted to have the domain just consists of three numbers, the number 2, 5, and 6. 2, that's a weird 2. 2, 5, and 6. And that's it. For the second example, g of x is equal to 3x plus 1, here the function is given by a formula, and we'll be working with functions mostly in this format. So we'll talk more about how to come up with the domain. Basically, you want to think about what are the possible values for x. Think of any real number you like. Is it always possible to multiply by 3 and then add 1? Yes, for any x, such a thing is possible. So you could write out all real numbers. Or if you know about interval notation, you can write the interval negative infinity up to infinity. Most often, we used interval notation to express the domain of a function. Because you may not already be familiar with interval notation, we want to go over that right now. But this is something that you may have already been exposed to in another algebra class. It's basically just a way to describe a set of numbers on the number line. So this graphic is taken from our textbook, but I just wanted to go over it in some detail. Taking a look in the middle, we have a graph on the number line of different sets of numbers. Here, the interval starts at A and extends upward. You should see a little arrow on the right to indicate that it keeps going. The second row, it goes up to, but not including A, and so forth. So there's different sets of numbers. How these would be written in inequalities is available on the first column. X is greater than A. Okay, that would be all the numbers bigger than A, which fits what we see on the number line. X is less than A. That fits what we see on the second line graph. The difference between greater and greater than or equal is just, is the endpoint included or not? Is A included? Is it part of the set or isn't it? In the case where it is a or equal to, either greater than or equal, or less than or equal, if it's one of those two, you'll see that it has a square bracket on the graph. If it is strictly less or strictly greater or less, you'll see it's a parenthesis. That's how we tell on the graph whether or not that endpoint is included. Depending on where or when you went to school, you might have had instead a system where it was open circles and then like solid circles to indicate that it was included. Our book uses the square brackets and parentheses way, and so that's the way I'll continue to show you. Okay. So then down the first column, we're seeing inequalities, and then the third column, we're seeing the graphs. In the second column, you're seeing interval notation, which is basically a way to describe in symbols kind of what you're seeing on the graph. If you think about how you might describe, let's take this first one, A. This is, would you describe this over the phone to somebody? You'd say, okay, well, it's a little blue line that starts at A and goes off to the right forever. It goes up towards positive infinity, right? That's what it says here in parentheses. It starts at A and goes up towards positive infinity. In the second one, the line starts at negative infinity and goes up to A. So in parentheses, you see negative infinity up to A. The only difference between those first two examples and the second two examples, again, is whether or not square brackets are included to indicate that the point A itself is included. The first four are what's called open-ended intervals because they extend off towards either positive or negative infinity. The second group of 4 are what are called bounded intervals because they have a finite or fixed start and end point. They start at A and end at B. And here they've listed it all 4 possibilities, ranging from both not including A and B up to including both A and B. Again, parentheses are used to indicate that the endpoints are not included. Brackets are used to indicate that the ends are included. That can seem really picky, but as you know, math is a very detailed subject, and so sometimes the littlest thing makes a big difference. So it matters whether you have a parenthesis or a bracket. Be careful when you're doing the homework to make sure and type a bracket when you mean a bracket or a parenthesis when you mean a parenthesis, because it's going to make a difference. Okay? All right. And then off in the last 4th column, you'll see each set of numbers written out in words. Okay. Important things to note about interval notation is that the order that the numbers are in matches the order that they would be on the number line. So for example, if we wanted this set of numbers 3 to 5, not including 3, but including 5. Sorry, that disappeared on me. Not including 3, but including 5. This would be in inequality form. 3 is less than x is less than or equal to 5. In interval notation, it would be 3 comma 5. It would be wrong if I wrote 5 comma 3. Okay, the numbers should be in number line order. The smaller number has to appear on the left. The other thing is this is an example of where in math we've used the same notation to mean more than one thing. If you see this 3, 5 and think, okay, well, is this like when you have the XY plane and you draw the point 3, 5? It's a similar looking notation, but it means something different. What we're working on in this section with interval notation, that is a way of describing a piece of the number line, and that's it. It's not the XY plane, a point in the plane. Okay. Sometimes we'll need to hook together 2 intervals to make up one set of numbers. And to do that, we use the U or union symbol to do it. So let's say that we wanted to think about the numbers that satisfy this statement. 1 is less than x, which is less than 3, which means x is between 1 and 3, not including 1 or 3. Or x is bigger than, let's make that bigger than 7. So that would be the interval 1 to 3. Notice I'm using parentheses in here because the 1 and 3 are not included. And then we're going to use the union sign, and then we'll have 7 up to infinity. With infinity, a parenthesis is always used. You don't use a square bracket with infinity. X is less than 7. So think about what that's got to look like. If it's less than 7, it's going to start at 7 and go down towards negative infinity. Go up to 7. Again, I have a parenthesis here because the 7 itself is not included. And then we have the x's between 4 and 10 inclusive. So those will be written with square brackets. And again, we're using the union symbol to join those 2 intervals together. Next up, we have -4 to -2, union 5 to 9. Okay. The order that the numbers are in matters when you put interval notation, and additionally, whether using the square bracket or round parenthesis makes a difference. So the interval notation is one way of specifying the elements of a set. Another way of specifying the elements of a set that is, in a way, a little more general is the use of what's called set builder notation. Set builder notation, because we're describing a set, starts with a curly brace and ends with another curly brace. And then the structure is curly brace, a variable, usually x is used, a vertical bar that is read out loud as such that or so that, and then some condition on x that indicates whether or not the number is or included within the set or not. So for example, if we wanted to describe the set of numbers that satisfy the inequality 4 is less than x, which is less than or equal to 5, we might write the set of all x such that 4 is less than x is less than or equal to 5. This can seem like a little extra, like clutter, like what does this give you that the first part doesn't? And the thing is that the set builder notation is more general and is useful for describing other sets aside from when you're talking about sets of numbers, or if you want to say something other than just a inequality. For example, you might want to say the set of all n such that n is odd. This would be a way of describing the set of odd numbers, for example. Of course, if we want, we can express intervals in either interval notation or set builder notation. And give another example. If we wanted to think about the interval, let's say I use a lot of 4s. Let's go with 7 to 19, union 20 to 30. Okay, how can I write this in set builder notation? So I would write the set of all x such that x has to be between 7 and 19. Forgot the x. That's part of it. Or the union can be read as or. X has to be between 20 and 30. So 20 is less than or equal to x is less than or equal to 30. Okay, so that would be the way to express the set in set builder notation. Our purpose for now of looking at set builder notation and especially interval notation is to help us express the domains of functions, which, as you remember, are the inputs to a function. Okay. So we saw in our first example, first example, that we were able to just list out the domains in this one, or the numbers in the domain 2, 5, and 6. If we have a function given by a rule, we have to have a way of knowing what is the domain. The domain is a set of inputs, and the key to it is the definition here. We want the set of all numbers x, for which f of x is defined as a real number. So you have to think kind of contrary. What would make it not defined? The kinds of things that might make it not defined would be division by 0 or square roots of negatives, things of that sort. So let's try here. All right, so here, f of x, we're going to try a first. F of x is 2x minus 11. So this one, there's no problem at all with f. You can plug in any number you want. Evaluate f of 10. F of 10, you would get what? 2 times 10 minus 11, that's 20 minus 11, or 9. Okay, was there anything special about 10 there, or could I put any number in? Multiply any number by 2 and take away 11. So here, we could write this in interval notation. It's going to be all real numbers, negative infinity to positive infinity, right? We could write the set of all x such that x is a real number. Okay, that would be the set builder notation way of doing it. Okay, let's try b next. B is a little bit more interesting. We have the function g of x, which is x plus 1 over x minus 4. This one, we can't get away with plugging in just anything. Which one can we plug in? Negative 1? Well, let's try negative 1. G of negative 1 would be negative 1 plus 1 over negative 1 minus 4. That would be 0 over negative 5, which is 0, right? That's okay. It worked out. The number that we can't put in is 4. If you put in 4, you would have 4 plus 1 over 4 minus 4, or 5 divided by 0. 5 divided by 0 is undefined, and so we can't do it. So we need to exclude that when we write out our domain. So in interval notation, it will be negative infinity up to, but not including 4. So I've got a parenthesis. We'll use a union symbol to kind of join two separate pieces together. And then we'll take over right after 4 and go from 4 up to infinity. In set builder notation, the set of all x such that x is not equal to 4. Okay. For C, we're interested in the absolute value of a number, minus 7. Can you take the absolute value of any number you want? Yeah, you sure can. So all real numbers for this one as well. Okay, for D, we have f of x, which is the square root of x minus 3. In order to get this to be defined as a real number, what has to be true? Well, if I tried f of 1, we'd have the square root of 1 minus 3, the square root of negative 2, which is not a real number. It's a complex number. Okay, so no, that's not going to work. So what do we need to have be true? X has to be, well, x minus 3 has to be at least 0, because we can only take square roots of numbers 0 and higher. So x has to be at least 3. Okay, so then we could write in interval notation 3 up to positive infinity. And then in set builder notation, the set of all x such that x is greater than or equal to 3. Okay. This one is a little bit different from E. In E, you'll see that we still have that same square root of x minus 3, but a big difference is that that radical is in the denominator. In F, is it okay to find f of 3? Can you find the square root of 0? Is that defined? It's 0, right? The square root of 0 is 0. But here, if we were to attempt to do g of 3, we would have 2 divided by 0, which again is forbidden, right? So that means that the 3 itself would need to be excluded. So we would just have the open interval, 3 to infinity, in interval notation. And then in set builder notation, the set of all x such that x is greater than 3, not just greater than or equal to 3. So you have to be very careful. You have to make sure that all of the kind of pieces to it are satisfied. You have to check, am I dividing by 0 and I shouldn't be? Are we trying to take the root, the square root, or other even root of a negative number, and maybe we shouldn't be? So you have to watch out for those things. Okay, so in the next video, we will continue with section 1.2.